Here's something that should bother you. We've spent the last several years building the largest neural networks in history, models with trillions of parameters stacked 80 layers deep. And the assumption behind all of it has been straightforward. More layers means more abstraction. Layer 1 handles tokens, Layer 40 handles syntax, Layer 80 handles reasoning. Depth is where compositional intelligence lives. But what if most of those layers are doing the same thing? What if the network you spent millions of dollars training is, functionally, much shallower than it looks? 3 papers from this week, combined with a decade of evidence the field has been slow to absorb, suggest exactly that. Let's go back to 2016. Veit and his team published a paper called "Residual Networks Behave Like Ensembles of Relatively Shallow Networks." Their insight was architectural. A residual network with n blocks doesn't define a single computational path from input to output. The skip connections create a binary choice at every block: go through the block or skip it. That means a 110-layer ResNet contains 2 to the power of 110 unique paths through the network. Now, those paths vary in length. Some go through nearly every block, some skip most of them. And when the authors measured where gradient actually flows during training, the answer was clear. Most of the gradient travels through paths only 10 to 34 layers deep. The longer paths, the ones that use 50 or 80 or 100 blocks, they contribute almost nothing. The practical test was even more striking. They deleted individual layers from a trained ResNet. In a standard deep network like VGG, removing one layer destroys performance. But in a ResNet, performance degraded smoothly and modestly. The network didn't depend on any single layer. It behaved like an ensemble of shallow subnetworks, and each one was somewhat redundant. The reviewers found the experiment solid but pushed back on the framing. ResNets behave like ensembles, they said. Whether they actually are ensembles, that remained open. And the field moved on. But evidence kept accumulating, quietly. That same year, stochastic depth training showed you could randomly drop entire layers during training, and performance actually got better. On a 1200-layer ResNet, dropping layers at random cut test error from 7.93 to 4.91%. Think about what that means. If each layer is performing an indispensable step in a sequential computation, removing a quarter of them at random should be catastrophic. Instead, it helped. In 2020, Albert took this into transformers directly. They shared all parameters across every layer, attention weights, feed-forward weights, everything identical at every depth. Performance dropped by about 1.5 points. That's it. If each layer were doing something unique, parameter sharing should have been destructive. It wasn't. Then, the LLM era made it impossible to ignore. ShortGPT in 2024 removed layers from models ranging from 7 billion to 70 billion parameters and found you could drop up to 40% before hitting a performance cliff. Not 5%, not 10, 40%. A 13 billion parameter model with 22 of its 40 layers removed actually outperformed the full 7 billion parameter Llama 2. Your transformer is secretly linear, explained why. Consecutive layers produce representations with a similarity score of 0.99 out of 1.0. Most layers are barely changing anything. The residual connection dominates. And in October 2025, on residual network depth, closed the theoretical loop. The authors proved mathematically that a residual network with n blocks decomposes exactly into a sum over 2 to the n subsets. Each subset is a computational path. Adding depth doesn't add compositional capacity. It expands the ensemble. Veit's observation from 2016 wasn't a metaphor. It was a mathematical fact waiting 9 years for its proof. So by February 2026, the groundwork was complete. The question was no longer whether transformer depth works through ensemble averaging. It was how far the consequences reach. This week answered that. Inverse depth scaling from most layers being similar, by Liu and colleagues, quantified the relationship directly. They analyzed Pythia, Quen 2.5, and OPT, and decomposed the standard neural scaling law into separate depth and width components. What they found is that the depth-dependent loss scales as d to the negative 0.30. That's a sub-inverse power law, meaning each additional layer buys you diminishing returns, significantly worse than 1 over n. And the mechanism behind it is exactly what the previous decade of evidence predicted. Most layers perform functionally similar transformations, and stacking them reduces error the way averaging reduces the variance of a pole. Not through composition, through the central limit theorem. The authors call this regime inefficient yet robust. Hard to break, but a terrible use of parameters. Think about it. If 70 of your 80 layers are doing roughly the same computation, you're paying for 80 layers of compute to get the effective capacity of something much, much shallower. They pin the blame on residual connections specifically, arguing that the skip connection architecture biases networks toward this averaging regime, and current training procedures don't push the network out of it. Now, this raises an uncomfortable question. If most layers are redundant copies doing the same thing, where does capability actually live? Is it built through deep sequential processing? Or is it already sitting in the pre-trained weights, distributed across the network, just waiting to be activated? The second paper this week provides a startling answer. Learning to reason in 13 parameters introduces TinyLoRA, a method for scaling low-rank adapters below rank 1. The authors apply it to Qwen 2.5, a 7.6 billion parameter model, and they train exactly 13 parameters with reinforcement learning. 13 parameters, that's 26 bytes. And they hit 91% accuracy on GSM-8K. Out of 7.6 billion parameters in the model, they changed 13, and it worked. With 196 parameters, they recover 87% of full fine-tuning's improvement across 6 math benchmarks, including AIM and AMC. The gap between adjusting 13 weights and adjusting 7.6 billion is remarkably, almost disturbingly, small. Now, this result does not make sense if reasoning is built through deep compositional processing. If that were the case, unlocking it would require modifying the computation at many stages. You'd need to reshape the entire pipeline. But it makes complete sense under the ensemble model. If the capability is already distributed across a broad, redundant ensemble, then a tiny perturbation can shift the collective output without modifying any individual member. The capability isn't missing. It's already there, just slightly misaligned, and aiming it correctly requires almost nothing. Here's the critical detail, though. This only works with reinforcement learning. Supervised fine-tuning needs 100 to 1,000 times more parameters for equivalent performance. Below 100 parameters, supervised fine-tuning barely beats the baseline. Why? Because reinforcement learning gets a sparse but clean signal, correct or not, and through resampling, it amplifies features correlated with reward, while uncorrelated noise cancels out. Reinforcement learning doesn't teach reasoning. It locates the reasoning that's already there. Supervised fine-tuning, by contrast, tries to absorb every detail of the demonstration, useful structure and noise alike, and that requires a much larger update surface. So, depth gives us redundant averaging, and capability is latent rather than built. That covers the vertical dimension of a transformer. But what about width? If depth is mostly doing the same thing at every layer, do the attention heads within each layer tell a different story? The third paper this week, Attention Sync forges native mixture of experts in attention layers, reframes something practitioners have observed for years. Large language models assign disproportionate attention to the first token, a behavior called the attention sync. The standard view treats this as an artifact, a quirk of softmax normalization. But this paper shows it's actually something far more interesting. It's a routing mechanism. The fraction of attention weight that doesn't go to the sync functions as an implicit gate for each head. Mathematically, this is equivalent to a mixture of experts router. Individual attention heads are the experts, and the sync determines which ones contribute to any given input. And the phenomenon we've called head collapse, where only a subset of heads actively contributes during generation, that's just expert collapse by another name. The numbers here are striking. Over 25% of attention heads can be zeroed out with no meaningful accuracy loss. And it gets worse with scale. Larger models with more heads actually show lower utilization rates. You add width, but much of that added width goes dormant. Now, put the depth and width findings together, and the picture should concern anyone building or deploying these models. Depth provides redundant averaging rather than compositional processing. Width provides expert selection through implicit routing, but without proper load balancing, a quarter or more of those experts sit idle. Modern large language models may be simultaneously too deep, with layers averaging instead of composing, and too wide, with attention heads collapsing into dormancy. The model is architecturally large, but functionally, it is much smaller than its parameter count suggests, and we are paying for all of it. Every layer that averages instead of composes, every head that stays dormant. That's compute, memory, and energy, spent on a very expensive voting scheme. Now, none of this means depth is useless or that transformers should be shallow. Ensemble averaging is robust, it works. But the claim here is narrower and more consequential than that. We've been scaling depth on the assumption that it buys compositional reasoning, and the evidence now clearly points to a simpler and less efficient mechanism. For architecture, the open question is whether residual connections are the root cause, and whether alternatives can escape the averaging trap. For fine-tuning, TinyLoRA raises a very practical question. If reinforcement learning can unlock reasoning with 13 parameters, are we massively over-parameterizing our LoRA adapters? And for inference, the attention sink finding suggests that head sparsity should be leveraged, not fixed. The decade-long arc from Veit 2016 through this week's papers tells a consistent story. 1. The field was slow to absorb. We built the largest models in computing history on the assumption that depth builds capability. The evidence says depth mostly builds redundancy. The capability was already there, and we've been paying an enormous computational tax to average our way to marginally better answers. Whether the next generation of architectures can actually do something different with their depth, that is the question these papers leave on the table.